Okay, now we're going to look at kinetic energy. And if you've ever taken a physics class, this might be one of the only things you remember from physics, which is something like 1/2 mv squared. You know nothing about physics except there's a 1/2 mv squared somewhere. Well, in case you care, this is where it came from. So we know that the little itty bitty work is equal to F dot dr. And you're like, I thought you meant it was an integral. Well, yeah, I mean, you can either do this, or you can say itty bitty work equals itty bitty F dot dr. Now we also know that F equals ma dot dr, right? So let's see, what else can we do with this? We know that, remember that other thing that was like ADS equals VDV thing? Right, maybe. So that means I can go like AVDVDS, like that. So I have D work equals M, and then instead of the A, and I am kind of hand waving a little bit, but I just want you to know that this comes from somewhere. It's VDVDS. And if we get rid of the dot product and we're like, no, we're not going to worry about the dot, we're just going to assume it's all in the same direction, we can just actually call that DS, and then the DS's cancel out. Again, this is kind of like fake math. And I have D work equals mass velocity D velocity. All right. Then I can integrate both sides, and then I get work equals 1/2 mv squared. Okay, but it's not really work. It's the area under the curve of work, which we have decided to label as kinetic energy. Okay, so this is a really, really bad math. This is bad math. Bad math. I mean, it's good math. It's the real math. I'm just like hand waving a lot here because you can get into more of this later. But the idea is that kinetic energy is 1/2 mv squared. And the change that you have in kinetic energy is the change in is basically the work that it takes to get from one place to another. Let's see, is that what it says? Yeah. So that's where the 1/2 mv squared comes from. If you ever wonder, it comes from calculus. Yay. And apparently we're doing it in terms of momentum. And since the momentum is this thing, we can do this thing. That's sure. Okay. I mean, I've never actually seen it that way, but sure, whatever. So I think that there's another way that we can express it, but let's see. So I actually don't feel like these questions here are terribly interesting. You know, what is the kinetic energy of a so-and-so running at a so-and-so? You know, their kinetic energy is 1/2 the mass times the velocity squared. I mean, that's about all you have there. So kinetic energy. Now, the reason that this matters is with respect to different frames. This is way, I mean, if you really wanted to get into this, this is something else. Translational kinetic energy, I'm not worried about that. Where we're going with this is the idea of the work energy theorem. Okay, so this is kind of where I was going with this with the equation. Oh, but they do show the math. Is that the work is the difference, the total work done is the difference in the kinetic energies. So like if I start somewhere and I end somewhere, I can either compare the work done or I can compare the beginning and ending kinetic energies, and sometimes that helps me solve problems better. The reason that I did it all from F equals ma is I've had students that are like, but I don't have to do this. I can just solve everything with F equals ma, right? Absolutely. You can solve everything with F equals ma. We're just showing you, like, this is a slightly easier way to do it, I guess. Like, you can solve all words by sound and blend, but if you just, like, memorize that this word means velocity, you don't have to get velocity, and just go velocity, your life's a little bit easier. So the net work done on a particle is the change in the kinetic energy. Okay, so let's see. Boopity-boopity-boo, boopity-boo, boopity-boo, boopity-boo. All right, so let's look at this problem. So frictionless track for a toy car, loop-de-loop. How high must it be placed to start from rest on the approaching section of track and go all the way around the loop? Okay. So basically, the idea is we're going to start at some kind of initial height. Height 1, I guess they're using y1, and height 2, but this is twice the radius, because that's twice the radius of the loop-de-loop. Okay, so I want it to be going just fast enough so that when it gets to the top, actually I'm going to go ahead and draw my free body diagram anyway, that it's barely touching. So if it's on a track, I want that normal force there to be 0. Like there's no normal force here, like n equals 0. I guess I could draw it that way. There's no force of it touching the track, and it's got a weight of mg. Now, I know it has an acceleration of v squared over r. Okay, so I can say, well, the sum of the forces in the y direction is negative mg equals negative mass times the acceleration. Those go away and that goes away, so the velocity squared equals g times r. So I'm going to save this for later. Okay, so now that is in theory something we did in chapters 5 and 6. Something we should already know how to, you should know this already. So that's a you should know this already part of the problem. And if not, that's okay, just go review it and you'll figure it out. Now for the work energy part. So the total work done to go from here to here, well gosh, I mean, I guess that it's not very far apart. So whatever h minus 2r is how far it's gone, and gravity, which is m times g, has done a good job, if we assume h is greater than 2r, and assume h is greater than 2r, then gravity has done positive work. The good news is if 2r is, then gravity will have done negative work, but say, good job gravity, you managed to successfully move something down. So the total work done, and so the only things doing work here is gravity, and then the difference in the kinetic energy. So initial kinetic energy plus, or sorry, I should say final kinetic energy minus initial kinetic energy. I'm doing something different in my head. Final kinetic energy minus initial kinetic energy. We say, okay, well, its final kinetic energy is 1/2 mv squared, because we proved that with calculus. Its initial kinetic energy would be 1/2 mv squared again, but it said it started at rest, so it's 0. Okay? Without too much angst, I'm just going to rewrite this prettier. mgh minus, and I know the m's are going to cancel, 2r equals 1/2 m, and the v squared is g times r. So in fact, not only do the m's cancel out, but the g's cancel out. It's going to behave exactly the same on Mars as it would here on Earth. So h equals 1/2 r plus 2r, which would be what, 5/2 r. So that's how high up we need to start to end up, yay, in the right spot. Does that kind of make sense? So for these problems, you're going to start like with the total work done on the object equals the final kinetic energy minus the initial kinetic energy, and you kind of play from there. All right, let's see what this does. All right, we have 40 grains of a bullet and a muzzle velocity and ignition rate. What's the average stopping force? Well, okay, so let's pretend that I know what I'm doing. Okay, so there's some kind of force that's bad at its job. So it's going to do negative work force. And it's going to stop after 8 1-inch pine boards with a thickness of 0.75 inches. Apparently I forgot to click unpause after I started my calculator app, which was funny because I worked most of the problem. So anyway, I converted 6 inches to 15.24 meters, or 0.1524 meters. Okay, so now let's see what I'm going to do next. So I know that the total work done, so work done is equal to the final kinetic energy minus the initial kinetic energy. Okay, so the job, the force sucks at its job because it's trying to stop it. I mean, it does eventually stop it, but it's still moving forward. So some force that's bad at its job over a period of distance of 1924 meters. Now the final kinetic energy of the bullet is 0 because it's 1/2 mv squared, but v is 0 because the bullet stopped, minus 1/2 m, oh, it has to be in kilograms, so 2.6 grams, and I need to go 1, 2, 3, is 0.0026 kilograms v squared, the initial kinetic energy. Oh, muzzle velocity is 335 meters per second. Okay, so it does give me that. 335 meters per second squared. I mean, meters per second, and then I square the whole thing. So the two negatives cancel out, so that's good. It would be weird if it didn't. So I have 335 squared times 0.0026 divided by 2, and then that would be divided by 0.1524, so 957.3. Let me see what that's even asking. So I got an answer that says 957.3 newtons, and what is that asking? What is the average stopping force? So that's how much in general the force of the wood has to resist to get the bullet to stop. So 960, is that what I got? Yeah, 960. Awesome. Okay, so I didn't even really, what I guess I'm trying to go is, it's not like a formula you look up and it's like this many boards is this. It's going to the idea of we got work done is final minus initial. Okay, and then you decide, is the work successful? So does it have a positive or negative sign on it? And then a lot of times for these, either the initial or the final kinetic energy is going to be 0 because they're just trying to make it easier on you. So it's not too bad.